Welcome everyone to this week's Autonomy Talks. This week is the pleasure to have with us Professor Shreyas Kousik, who is an assistant professor in the George W. Woodruff School of Mechanical Engineering at Georgia Tech. Some bio for Shreyas. So he completed his Bachelor of Science degree in Mechanical Engineering from Georgia Tech in 2014, and then his Master of Science and PhD degrees in Mechanical Engineering from University of Michigan and Ann Arbor in 2020. Then he was for a while a postdoctoral scholar at Stanford in the Aeroastro department. And his research in general focuses on full stack robot safety, seeking theoretical foundations, but also numerical representations which enable robots to make safe decisions quickly. As you've seen in the bio, his work has been recognized by a number of awards. And today he's going to talk about the right stuff, which I like, representing safety to get robots out in the real world. And this falls perfectly within the scope of this series. And therefore, I'm very excited to give you the stage and hear more about it. Go ahead.
Thank you.
Shreyas.
Yeah. Wonderful. Thank you so much for the kind introduction and the invitation. Yeah. So, hi, I'm Shreyas. I guess usually when I do this talk in person, I ask people, who does robotics, but instead I'll get into it. Okay, so we've seen this promised every year, right? Where's my self-driving car is a question that we've all been encouraged to ask, and industry keeps telling us it's coming. But every year you can find a new article with new caveats because it's a genuinely hard problem. And I like to look at not just engineering, but how engineering fits into society and how we can influence even the legal code. The other thing I'll point out, one of the key challenges we have in engineering here in the United States is this interface with diversity, equity, and inclusion, or DEI. The population of people who are often encouraged to or able to become engineers is very different from the general population. So it's interesting to think about how society that's made up of everybody should trust engineers when we say that something is safe, or we say that we're going to put a 2-ton robot on the road and it's going to be okay. From this large perspective, obviously we can't solve all of the problems, but we engineers, especially as academics, we can formalize and implement notions of safety. And by creating the setting in which we can test whether robots should be everywhere, I think that's the way to really assess, how we can impact society positively. So before I get into the technical content, I'll quickly show you a couple of videos. So here is in collaboration with the University of Sydney. This is a little autonomous golf cart. Well, it wasn't autonomous until we put the algorithms that I'll talk about today on it. And here you see it autonomously avoiding some planters and some people and getting to the end of this long walkway. The fun part is, in this case, safety is collision avoidance. And I apologize, the video froze. Well, it looks like there's a bit of lag on my end. I don't know if you see it on your end, but whatever the case, the robot is able to drive around, avoid some boxes, and adapt to this changing environment in real time. So the neat part is we can make a formal guarantee that this will happen before we actually run the robot. That makes it much more reasonable to test. I mean, here you can see I am an obstacle, right? And I have no worries about being in front of the robot because I know it will, in this case, safely stop. Unless I hit it, it will be okay. This is important because this philosophy can convey to a bunch of a variety of robots. So out-of-the-box methods, I mean, this is a bit of a contrived example, but we were surprised to see that, a generic solver, if you start in a singular configuration, it may just converge to a really, really bad solution. But in our case, we were able to solve that singular configuration problem as well, but I wanted to show this little video of, a dynamic obstacle and making a safe decision. Here I accelerate the end of the video just because the robot is moving in the plane of the camera, so it's a little bit hard to see it. But the point is, we can do better if we're very careful about pre-defining safety and getting it to work on the real robot. This also isn't always necessarily just about, saving the world. Sometimes it's just embarrassing on public television when your robot falls over. I feel a little bad that this poor video of Cassie at Michigan has really gotten the runaround, but at least we won that football game. The methods I talk about today will be, they're being put already or extended onto legged robots such as this Digit. So here Digit is autonomously deciding to move around these obstacles, and there's a guarantee that it won't fall over as well. The neat part is we can by being clever, we can start to create these methods that let us put robots out in the real world. So the vision here is formalizing safety to enable wide deployment. And obviously, you have to ask, how do you define safety? And then defining it on the whiteboard is one thing, but actually getting it to work on the robot is a whole separate problem. In this talk, I'll discuss reachability analysis methods and geometric methods that we've used in the past to answer these questions. Okay, so first off, how do we define safety? And I like to think of things in terms of this full stack or the full autonomy stack. As a running example, I'll use this autonomous car. So our hardware may be the car itself. And let's suppose that we have to get to this global goal, the green star down at the end of the road. The first challenge is to sense the things around us correctly, and sensors are inherently limited. So safety in the sensing world means correctly detecting or conservatively detecting and predicting the motion of others. I won't focus too much on that in this talk. That's something for ongoing and future work. Instead, I'll focus on this planning and control problem. On the planning side, we usually create intermediate goals such as waypoints, and then use a simplified planning model, as I'll call it. So I'll denote that with a script F. This planning model is usually a simplified description of the vehicle or robot dynamics. And then if we were to track those plans, because it's simplified, we don't do a perfect job. So we can try and incorporate a much more accurate physics description if we were to simulate this robot, and I'll call that the high fidelity model. If we can compensate for the mismatch between these models and then still execute plans that are not overly conservative, we can safely get to global goals. I'll call this mismatch tracking error. And the idea is that safety throughout this talk will just mean collision avoidance. We can get to more sophisticated notions of safety going forward, but collision avoidance is one of the really hard ones. It's non-convex, it's non-linear, it shows up in workspace. So it's a hard problem to solve. So in this talk, I'll focus on safe, real-time, and even optimal planning and control. This is really the focus of my past work, is all this planning and control stuff with the focus of getting it working on real hardware. And more recently, we've managed to think about sensing with some guarantees, but it turns out it's very easy to get very, very conservative results where you think your robot could be anywhere. So this is a key challenge for future work. Now, I can't talk about everything, so I'll focus on these three key ideas. In particular, this broad idea of reachability-based trajectory design. So I'll introduce where it came from and how we started out in this area. And then how to exploit the safety layer. I'll exploit it in two different ways. So one is on the optimization side, designing a careful optimization procedure to enable really, really fast and safe motion planning. And then throwing learning into the loop. So how do we use the safety layer in collaboration with an RL agent to really outperform any human-tuned way of doing this motion planning? Okay, so feel free to interrupt during the talk with questions, and I'll go ahead and get into the first part. I'd also like to say this is all collaborative work. I tend to not like working on my own in an office somewhere. So this is the most fun part about research for me, is really meeting cool, smart new people and getting to work with them. Let's go to the safe planning problem, and we'll focus on just this this left part of the autonomy stack, so planning and control really. We usually want to minimize some arbitrary cost function while picking a control and state signal subject to our dynamics and being outside of obstacles. Enforcing this constraint of being outside of obstacles is non-convex, and we have to enforce it, both of these constraints at infinitely many points in time. So numerically, as easy as it is to write down this problem, it's very hard to implement numerically. Often one way to do this is to think about the planning hierarchy. So at a high level, you can create waypoints, pass these to a trajectory planner or mid-level that can plan to intermediate local goals. And then at the lowest level, your tracking controller will try and track those trajectories accurately. And as an example of the high-level planner, many of you are familiar with RRT or A*. Often in the autonomous driving case, we can think about really leveraging the physics of the vehicle. So one example is this state lattice idea, where a point in this parameter space on the left corresponds to motion plans or path plans in the space on the right. I'll use this big K to denote parameters throughout the talk, and then big X to denote a state or workspace. If we have an obstacle in this case at the high level plan, we can use it to eliminate plans that are unsafe. But to compensate for the uncertainty in our motion or the fact that our vehicle occupies volume, we have to dilate these obstacles by some amount. And so there's this conservativeness trade-off of how much to dilate to be safer versus making it so that we have fewer options that we can pick from. We can also think about enforcing safety at the lowest level. So you may be familiar with control barrier functions or model predictive controllers, and I'll give you a cartoon overview of these again. I'll also point out, I like cartoons a lot. Please understand, anytime you see a cartoon, there's math underlying it, but I want to convey the high level idea. And then I'm happy to talk about the math, either by answering questions or offline. So for one way to think about control barrier functions, and certainly this is, you shouldn't take this as gospel truth, but this is one way to think about it. Imagine that we have a nominal control input. So in this case, our vehicle just will go straight. But in the presence of an obstacle, we want to make sure that we stay outside of it. So I want to certify that this green set is control invariant, or I can stay within it. We can, if we can find a control barrier function, often this turns into a polytope of constraints on our control input that let us adjust unsafe controls to keep us within this safe set at all times. If we want that safe set to be much larger, it can often restrict our controls much more. So there's a bit of a safety versus performance trade-off, even though we can have a very strong safety guarantee. One way to start to get away from this trade-off is through carefully designing MPC. So if I had an initial guess, I want to solve this exact problem we wrote down earlier, but while really considering the high fidelity dynamics, an accurate dynamical model of my robot. A solution may look like some trajectory in control space and a corresponding trajectory of the high fidelity model of the vehicle. But of course, directly solving this nonlinear, non-convex program at runtime is very, very challenging. Instead, we can try to convexify our constraints. So create a tube of convex shapes to stay within. And typically we have to discretize in time. So we can't directly represent or put constraints on the continuous time trajectory very easily. And computing these convex tubes is its own challenge. I'll present RTD that thinks about safety at this middle level. And so we get costs from the high level planner, and we know something about the performance of our low level controller, and we enforce safety in the middle. In particular, we want to consider tracking error. So we know that we're planning with some incorrect model of our robot. We want to incorporate continuous time and space collision avoidance. And we want to represent our obstacles in a way that enables really fast trajectory planning. And in particular, it's cute, but these are the contributions that we'll call RTD. Okay, so how do we start? We begin by computing what I'll call the forward reachable set offline. And you can think of this trajectory parameter space, so similar to the state lattice, but now we're parameterizing trajectories, not paths. And each point in that space corresponds to some short motion plan of the robot. I'll give you an example of what these look like shortly. If I can compute the continuum, this reachable set in state space corresponding to all possible trajectories, I can do this offline while incorporating tracking error or this model uncertainty into my computation. Given that object computed offline, we can use it online as follows. We can intersect it with unsafe sets and then project that intersection into our space of parameters. And then given something like a cost function, so reaching a waypoint that can also be projected into the parameter space, we can basically treat the obstacles that are in workspace or state space as constraints in our planning space, and know that the corresponding tube of motion around our nominal trajectory is actually certified to be collision-free. This is despite the fact that our vehicle may not perfectly track these trajectories. Every t-plan seconds, we can rinse and repeat this procedure. So what I mean is that we're replanning over and over and over. What we'll do is we'll identify constraints, create a cost function, such as reaching a waypoint, optimize over that cost function subject to the constraints, and know that the corresponding tube is collision-free, despite uncertainty.
Shreyas,
Go ahead.
To stop you. There was a raised hand by Chui Zhang.
Yeah, go for it.
I guess this was a question.
Yes, can you hear me?
Yep.
Yes.
Yeah, go ahead.
So just wonder, what's the axis of the parameter space? Like, what would be the unit, or like just in general, what's the axis represent?
That's on the very next slide. Good question. A parameterization that we found really useful for vehicles is a speed and yaw rate that are profiled through time that break after the time t plan. So if you're replanning every t plan seconds, then your speed and yaw rate, or your nominal speed and yaw rate, are changing. And you may have noticed that we're solving a nonlinear non-convex program anyways, and I complained about that, so we'll solve that later in the talk. If I can't solve that problem fast enough at runtime, then my previous trajectory parameterization breaks to a stop. This is the notion of a fail-safe maneuver as well. So this has been explored a lot also by researchers in Munich. So the idea is like, we can parameterize something that does something meaningful, like go at a certain speed and turn at a certain rate, and parameterize the brake and maneuver all in one small set of numbers. And that reduces the size of the space that we're searching over, this space K on the left. So I hope that answers your question, Kong. Also nice to see you. Thank you for coming to the talk.
Of course, thank you.
Okay, so let's take this parameterization and run with it. Now what we want to compute is, given our planning model, we want to compute the tube around our nominal trajectories or our planned trajectories that compensate for the uncertainty in our system. And we'll do this by introducing what I'll call a tracking error model. So G here is a function that captures the tracking error, and then D is a function that sweeps, so it's just a function of time that maps to plus or minus 1, so it sort of sweeps out the volume around this trajectory. And to give you a more visual understanding of what this looks like, you can imagine that G overbounds sampled tracking error trajectories through time, and then D lets us sweep out the volume. Given a polynomial representation of the planning and tracking error models, we can try and then compute this forward reachable set object. In particular, one way to do this is to use a sums of squares program to find a polynomial W, such that any point in the FRS, so any point that's in the blue set, evaluates the greater than or equal to 1 on this function W. Now you can imagine that this exactly will show up as a constraint for online optimization. We care about W evaluating to less than 1 for our choice of trajectory. So this is how we use the forward reachable set at runtime, at least in the vehicle case. Given an obstacle, we want to project it into the planning space on the left, so KU for unsafe. The idea is to solve this problem of finding some K that is outside of the unsafe set, subject to an arbitrary cost on those parameters. And the issue is checking if a point is unsafe means that checking if any point, if there exists some point in that obstacle that intersects with the unsafe set. So we have to evaluate our polynomial W on every single point of the obstacle, and this is numerically challenging. Instead, what we can do is create a discretization of our obstacle, so a finite number of discrete points parameterized by a spacing R and a buffer B, with the physical intuition that our vehicle or robot more generally cannot squeeze between these points. The critical thing is that these values exist and they're bounded for any compact body meaning our robot, not the obstacles. And as long as the obstacles are polytopes, then we can compute this pretty easily. The cool thing is now what we can do is we can evaluate that W polynomial on a finite number of points to check whether we're safe or unsafe. And you can imagine this as taking each of the discrete points that you see on the right and mapping them to a corresponding set on the left. And that overbounds, or it covers our true unsafe set, such that if we optimize outside of it, we're good to go. Now, we can also do this in the dynamic obstacle case. So in this case, we have to discretize with some delta T, as well as the point spacing R and buffer distance B that you saw earlier. And just to hint at this idea of, I'm interested in the longer term in the legal aspects of autonomous driving or widespread robotics. In this particular paper, we took the idea that safety means we're not at fault in a collision, and we turned that into collision avoidance constraints and a constraint on our braking behavior. The cool thing is the hard constraint I've seen is almost always this like non-convex obstacle avoidance constraint, but you can start to add other constraints as well for online planning that let you start to respect or obey the law, and the overall framework doesn't change very much, so it can compensate for these more general notions of safety. Okay, so what does it actually look like? We found that it outperforms a variety of other methods while ensuring safety. I will point out a caveat here. It's very hard to set up a fair comparison. I mean, this is generally true. And I think that now we have like the Arch challenge for hybrid systems or reachability analysis. So there are efforts underway to create fair comparisons across a variety of methods. And so with that caveat in place, I'll still present these comparisons, but know that just setting up the comparison fairly it's still a challenge in this field. Okay, so before we put it on hardware, we would definitely want to test it in simulations. So this is a Ford Fusion model that Ford Motor Company kindly let us use in car sim. It's driving up to 55 kilometers per hour, which is the speed limit on this road, and then autonomously deciding to avoid these orange boxes. So in this case, we just wanted to test the static obstacle avoidance. We're not explicitly asking it to change lanes. It's constrained to stay on the road and then constrained to avoid these obstacles. And certainly you can see some conservativeness. Our reachable set bleeds out into the shoulder a little bit. So reducing that conservativeness is a big challenge going forward. But what we did is we tested it on this 1 kilometer long track to do 10 laps with random obstacles and replan every half a second. I will point out that Ford has taken this method and now they're replanning every, at 50 hertz, not at 2 hertz. So that was the engineering problem, not the research problem. And to complete this 10 laps, we found that RTD was able to do it 100% of the time while planning in real time. We also compared against an RRT based on one of the DARPA challenge RRTs, and then against a GPOPS2, so model predictive control solver that had access to very, very accurate dynamics model. I tuned this RRT and there's one crash where it couldn't break in time. I'll point out, like, you can absolutely use a much more specific version of high-level planning or path planning to solve the same problem. But the point of this was to say RRT and MPC in this comparison had a safety versus performance trade-off. And we were starting to see a decoupling of that. We were able to get performance while also getting safety and planning in real time. And this is the beginning of this work that made me feel really excited that we're onto a good way to not just write down theoretically what safety means, but also to put it on the actual computer, on the hardware. So that's what, now you can see this video again, and this is exactly what's going on. This vehicle is planning in real time. Its reachable sets are constantly being recomputed to avoid obstacles, and it's able to navigate autonomously through all of these planters. The cool thing is, in comparisons, we were able to do this in a bunch of dynamic and random environments. In this case, we're assuming that we receive predictions of other agents, and actually generating those predictions is very hard. But in comparison to a state lattice, so something that's actually exploiting or is defined around the dynamics of the vehicle, we were able to outperform it both in terms of crashes and reaching the goal. What we found is that it took us longer to reach the goal in these random environments. So by driving a little bit more carefully, but by making that safety guarantee, we were able to improve the rate of a mobile robot moving through a dynamic world. We also tried some more structured environments. So here's unprotected left turns where the cars and pedestrians are simulated. They don't care about each other. They're just doing what they're going to do, and we assume some prediction of them. But the cool idea is that we can validate this entire left turn maneuver before executing it. In this case, we saw that just tracking that, so running a collision checker and then tracking this trajectory that was predefined still resulted in some crashes. And certainly the more we tuned it to avoid crashes, the less it was able to complete the task. Whereas with our method, we were able to just make the left turn in 99 out of 100 times, and one time we just never entered the intersection. Surprisingly, as you saw earlier, we're more patient. So the idea is you can wait until your whole maneuver is validated, and you're able to actually get all the way to the goal. Again, I'll point out that we're still pretty conservative. Our reachable set is a lot bigger than what you would really think the car is going to execute. So on the numerical side, there's a lot of work to be done in reducing that conservativeness. But we did this on a whole bunch of different wheeled robots in a bunch of different settings. And we found that across the board, we're able to do this. And we decided to really, put some skin in the game here. So in this case, we asked the Segway to come towards the camera, and we faced away from it. Honestly, this is the first take. We didn't know what was going to happen. But the robot, autonomously drove around us, and it's a 200-pound robot moving at, over 1 meter per second, so it would hurt. But the nice part is what the takeaway is, we're able to start thinking about societal trust or putting robots out around people because we have a safety guarantee. Of course, we haven't solved all the problems. Reachability analysis is hard. It takes a lot of compute. And in this case, we're assuming some open loop interaction. So the idea is that the predictions of other agents moving around doesn't actually change when we create our short trajectory plans. Sometimes that's actually a valid assumption, like in traffic, often people don't interact with each other. But then the last thing that we had to solve is this non-convex nonlinear program at runtime. And that's really, really challenging, right? So I'll address a method that we introduced that can start to, that can provide optimality and runtime guarantees on this challenging optimization. So this brings me to the second part of the talk, the parallel constrained Bernstein algorithm. And this is in collaboration with some lab mates at Michigan and Ram Vasudevan, who's a professor at Michigan. So our goal was to leverage the safety layer to get performance out of the system. In particular, at runtime, we're solving this program. We have all of these constraints. We want to minimize some arbitrary cost on our trajectory parameters subject to this W polynomial being less than 1 on all of our discrete points. This is a pretty low dimensional problem. It's in the example I showed earlier, K is actually only a 2-dimensional space, but we have hundreds of constraints. We're discretizing all of the, usually an occupancy grid or polytopic representation of the world around us that turns into hundreds of discrete points. If our cost is a polynomial, so if we take a Taylor expansion of our dynamics and then minimize the squared distance to our, some waypoint, that's an example of a polynomial cost, and now we have polynomial constraints. We can start to exploit the structure of this problem. And to put this in context, we propose this parallel constrained Bernstein algorithm that has to do 3 things. It has to be fast enough for real time. It has to get us an optimal solution, and it can't use very much memory. What we were using before in RTD was actually just MATLAB's fmincon solver, which is fast and doesn't use almost any memory, but it never has a guarantee of optimality because it's a gradient descent-based solver. On the other hand, this bounded sums of squares or BSOS solution. So this is using, directly optimizing over polynomials, and you can get the optimal solution, the guarantee, but it takes a long time and it tends to use a lot of memory for large numbers of constraints. And then finally, a branch and bound method. So the dividing rectangles method, which in the unconstrained case does give you optimality guarantees and doesn't use any memory. We found that it was pretty fast, but not the fastest. Instead, we proposed this parallel constrained Bernstein algorithm, which is a different type of branch and bound to solve this issue. So to introduce this, I'll point out what Bernstein basis polynomials are. Here you see the Bernstein basis polynomials in 1 dimension up to order 4. And the idea is that you can explicitly parameterize any polynomial in this basis. The math, writing all the math out doesn't matter so much as this idea that the polynomial value, so any polynomial expressed in this basis has its value over an interval defined, bounded by the coefficients in this representation. In particular, this hints at how you might use this for optimization, but I'll illustrate it. So imagine that our entire interval is now represented, or our polynomial cost is represented in the Bernstein basis, and the upper and lower bounds are represented by this blue box. We can compute these coefficients with a linear transformation, and as we subdivide our interval, we get tighter and tighter bounds on the value of, in this case, our cost polynomial. So you can imagine that our upper bound and lower bound have shrunk a little bit, and then we can maintain an optimal value estimate as the least upper bound, and an optimizer estimate as the center of our of whichever interval contains that least upper bound. So this is the standard branch and bound approach. The key idea is we're using this Bernstein representation. By branching and bounding, as you would expect, you can start to eliminate areas that could never contain your optimal solution. And then eventually you're guaranteed to converge on the globally optimal solution, in this case shown without any constraints. The nice part is that we can parallelize this while incorporating constraints, and then prove the convergence rate and show that it actually helps us on a real robot. In terms of the convergence rate, as you increase the tolerance required of getting to optimality and constraint satisfaction, the growth is logarithmic, which is what you'd expect from a branch and bound algorithm. But the takeaway here is really that you can plan optimally in real time. So don't worry too much about the math. Just think about this as like knowing how many iterations you have to run on your computer to get to your solution before you even put it out into the world. And of course, as I said earlier, we're not going to just directly put it on a robot. We compared this against the other algorithms that I mentioned earlier on a variety of benchmark problems. So here's a two-dimensional problem that's notoriously non-convex and has hard optima to find. On problems such as this, we often found we had lower optimality error than other methods for the same tolerance. And then we were able to solve nearly as fast as fmincon by parallelizing on a GPU. In other words, we can outperform these other solvers, so it validates the idea that we should put it on a robot. And that's exactly what we did. All right, so in this video, you'll see, one sec. All right. This is in direct comparison to fmincon. So here I set up a deliberately challenging scenario. The robot's cost function is just to get to the end of the hallway. And then I counted how many times it stopped safely when planning with NLP or nonlinear programming solver. So this is fmincon. And then it spends 43 seconds. The same trial with the Bernstein algorithm, we count the number of emergency stops, and it's not perfect. This is a hard scenario. And it doesn't already, it didn't know where the obstacles would be, but we're able to significantly reduce the number of stops and the total time spent on getting to the global goal. So to really push this, I created a scenario that I thought that the robot would never be able to solve, and then tried out fmincon. So it immediately starts converging to local optima and making bad decisions, and then immediately gets stuck. And that's what you see here is the robot, when it gets stuck, I programmed it to just wiggle in place and see if it can start to get out. So then I manually drive it to somewhere that I think it can get out. It gets stuck again. And then I have to manually drive it again to get it to go through this very tight corridor. The corridor is just wider than the robot. And then arrogantly on the first take with the parallel constrained Bernstein implementation, it just worked. With the exact same cost function, exact same constraints, it was able to make much better decisions with this optimality proof. So the idea is we can do safe, real-time, and even optimal motion planning and consider a fast solver for, so we're proposing this fast solver for low dimensional and highly constrained polynomial optimization problems. This is a generally useful tool, but I'm glad to see it worked on the robot. Again, we haven't solved all the problems in the world. This requires a GPU, though I don't think we ever used more than 11 megabytes of GPU memory. And then the thing I want to talk about next is hand tuning this high-level planner and solver. So I mentioned at the beginning of the talk, we have this notion of a high-level planner like RRT or A-star that can tell us waypoints that the robot should reach. That still had to be hand-tuned. We just had an optimality guarantee in the intermediate mid-level solver. And this is, I think, the exciting part where we can start to bring reinforcement learning into the fold. So this method I'll propose is called Reachability-based Trajectory Safeguard. We did it originally at Michigan with Simon Xiao, Chao Chen, and Ram, and then Amr, Mahmoud, and Marco and I continued this idea along with Kala Johansson and Grace Gao at Stanford. So this is an ongoing idea of creating a safety layer for reinforcement learning, but I'll present just the preliminary work in this space. So the goal is to learn to leverage these safe representations that we set up in the first part of the talk. In particular, if I hand tune A-star or something, it may do a bad job of generating waypoints, but that can lead my lower level parts of the autonomy stack to converge to poor solutions. And in this case, my trajectory planner may actually converge. If I use something like fmincon, it may converge to an infeasible solution. However, I can always just perform a bit of gradient descent on my constraints and then get to a nearby safe solution. So the idea is to replace hand tuning of waypoint selection with a reinforcement learning agent, and then adjust if it makes an unsafe choice using the reachable set methods that I introduced earlier. Now, creating this learning feedback signal was one of the challenges. And then also, obviously, tuning an RL agent is not necessarily any easier than hand tuning an A-star waypoint planner. The nice thing is that, at least what we noticed is, the RL agent was able to outperform us. So in this case, you'll see a baseline RL agent. We'll drive around and it'll crash into stuff to learn about what not to do. Also, I see a question in the chat. One sec.
Yeah, no, it's
okay, yeah, that's a good
question.
comment.
It's a reflection, I think.
Maybe you need the Bernstein algorithm for life decisions, only for local short time horizon decisions. RL is better for long time horizon decisions, and that's what we see here. So this is in the during training, right? So the vehicle is not really making good decisions, but what we're able to do is we're able to adjust. So here it makes an unsafe decision and then has to brake to a stop safely. And so the dashed yellow line that you see is the RL agent output, which may be unsafe. And then the solid black line is the corrected or adjusted safe trajectory plan. And while training through this method, we noticed that basically we're able to outperform my personal hand-tuned RTD solver. So that was a little embarrassing for me, I guess. But on these, we would create some pretty hard highway driving scenarios. And I thought we were doing great. We solved 90% of them with RTD, but the RTS, the safety layer with the reinforcement learning, was able to get to 100% of the goal. So it was able to fully exploit the safety layer while still, accomplishing its task. This also accelerated planning time. So you can think of this as taking a really good guess at solving that nonlinear, non-convex program. And so only a couple of gradient descent steps get you to a really good solution. And then, of course, we wanted to validate that this is safe. So obviously the safety layer is the same as RTD. It just prevents the vehicle from crashing. So this is my very bold claim. And I in more recent years, I don't necessarily agree with this anymore, but at the time it felt like tuning the RL agent was actually easier because we didn't have to worry about the safety versus performance trade-off. And so in some sense it is easier, but you're again, still dealing with a hyperparameter search. So there are challenges. Now, the fun thing is that this worked across a variety of robots. So here again, you'll see the yellow dashed line is the output of the RL agent, its plan. We correct it to a safe plan. And then here, the final trajectory is actually overlaid due to a plotting confusion, but know that the trajectory itself is actually being generated at runtime by the drone. This is also, we deliberately reduced the density of obstacles to make it possible to see what's going on in one of these example scenarios, but the actual scenarios were much, much more dense in this little flight tunnel. Okay, so that's what we've talked about, is this idea of incorporating safety through reachability and then leveraging the safety layer in two different ways. PCBA lets us exploit it for performance, in particular optimality and real-time planning guarantees. And then RTS lets us exploit it for long-term horizon planning. So improving task completion over the long horizon by knowing that we're implementing safety in a short time horizon. Where do we go next? Like I said earlier, I want to formalize safety to enable wide deployment. And this is what I'm planning on working on. So I just started as a professor at Georgia Tech. Actually, I'm very glad that some of the students that are joining me in the fall are actually here attending this talk. So thank you for making the time. This is what we're going to work on. So first of all, I think bringing learning into this motion planning problem is really interesting. And then robustifying perception, I've worked on it a little bit, and then I've just found that it's really hard. There's no nice answers, which you would expect. But the reason to work on these two things is actually to unite them in this notion of co-designing the various components of the stack, even the hardware, to make a robot have its own notion of safety. And I'll give you a flavor for what each of these directions looks like. So in learning to plan safe motion, one of the things that's really challenging is computing these reachable sets for really high dimensional system models. So if I have a very complex system, like a manipulator arm subject to uncertain dynamics, it's hard to compute reachable sets. And then even if I can compute that offline, it's not correct when my model changes at runtime. My road friction may change, or something about my environment can change. And so here's an example that we saw. Here, my lab mates bravely volunteered to be obstacles for this little quadrotor that's running RTD. And I deliberately asked them to walk slowly so that it would force an interaction. So we see the drone kind of do this little spiral maneuver to, wait, and then eventually it reaches the goal. But in fact, I didn't know that there was an air conditioning vent open before we ran this experiment, and it pushes the drone out almost out of its reachable set and into the obstacle. Obviously, this is not good, and it's fundamentally down to modeling error. Our models were all fixed offline, including our notion of tracking error computation, but the dynamics changed at runtime, so our reachable sets were no longer valid. I'd be very, very excited, and we've started working on this, about like adapting our reachable sets at runtime based on a changing model. And a paper that we've just recently put on archive also considers robustness to model uncertainty in a different way. So here we have a manipulator trying to move this weight from one side of the table to the other, but it doesn't actually know the mass of the dumbbell. It can still be robust to this type of uncertainty while making a guarantee that the dynamics, not just the kinematics of the arm are safe. Of course, none of this means anything if the robot can't tell what's around it. So I've started thinking about this idea of verifying learned perception models, and really verification on the perception side alone doesn't really make sense unless we think about it in the context of planning and control. So something that we started doing, and I would be excited to talk about this more offline, is learning to communicate safety information in smart cities. This is also very closely tied in with the notions of society and law. So something that's happening in Atlanta is this notion of the Operation Shield. They've put thousands of additional cameras everywhere with the idea of doing predictive policing throughout the city. And it makes some people feel safe, but other people feel much less safe. So if we're going to propose that cities are watching everything we do, I think we should approach this very, very cautiously. And in this case, we tried doing a self-supervised approach. So any bias that's present in the data will actually continue to be present in the deployment of such a system. And talking about these issues is, I think, critical. A different way to think about perception is in the notion of how you represent your scene. This is not my work. This is work from some colleagues at Stanford who showed how to do MPC through a NeRF, so a neural radiance field. And I'm curious to start to see, how do you actually guarantee collision checking? And there was a really good SIGGRAPH Best Paper Award recently that showed how to make some guarantees about NeRF training and evaluation. So this part of the community is, I think, very, very, it's very exciting to think about these problems and know that if we can target the outputs of our perception stack to be particularly useful for planning and control, then we can get some nice safety guarantees despite actually, avoiding conservativeness or decoupling safety and performance, as is our overall goal. And this brings me to the big idea that I hope I get done in the next 5 to 10 years. Can we learn all these components together, and can robots teach themselves to be safe? And maybe we'll solve some cute problems. So this is a really high dimensional control problem where you saw this robot hand solve a Rubik's Cube autonomously, but it also dropped the cube about 30% of the time, I want to say. So it would be very interesting then to model grasping these types of objects and making sure that we're never going to, we'll safely interact with it without ever dropping it, for example. We've also seen more extreme dynamics. So TRI has been working on this idea of safe drifting, and it was kind of cool to see these cars in person. This is awesome. I mean, it's really, really cool, right? This is working at runtime, doing these super complex nonlinear control, but in this case, they know exactly what is around the robot, and they know where exactly the robot is. And as soon as you start to bring in certainty, and I think it's much harder to plan and execute these dynamic motions, but by co-designing the parts of the autonomy stack, I'm very excited to potentially plan these extreme or agile maneuvers at runtime. So ideally, as I push this research forward and I work with smart people like yourselves attending this talk, instead of asking, are we there yet in terms of do robots work, we'll just ask that question directly to our autonomous cars. And with that very, very cheesy joke, thank you so much. It's been a pleasure getting to share this work with everybody, and I'd be happy to take any questions or comments.
Thank you, Shreyas, for the great talk. Let's open now the stage for questions. You can either type in the chat and I would read it for you, or you can raise your hand and I'll give you the word. Yeah, and go ahead. You can start.
Okay. Hey, thanks for the great talk. I really enjoyed it. So one maybe very high level question is, so now you're considering safety as collision avoidance, but in general, safety is more than collision avoidance, right? Traffic rules are more than that. So are you also planning on thinking about how can you integrate more complex notions of safety in your framework, or not at this point?
Yeah, so in that future work stuff I showed about the manipulator, we also incorporate joint torque and speed constraints. The one thing I've noticed is that one of the hardest constraints is actually collision avoidance in workspace, right? So there's a nonlinear map from state space to workspace, and it's also a set valued map. You have to consider the occupied space of the robot. So I would argue that a collision avoidance constraint in workspace respecting the geometry of the robot is one of the hardest types of constraints to implement. And if you can implement that one, it turns out the other ones are often similar looking or even more convex looking. And then this is just from experience with things like actuator torques, speed limits, other types of convex looking constraints. One constraint that is really, really hard to implement that I really want to work on more, and we recently submitted a paper on this, is dynamic collision avoidance, where the predictions of other agents are conditioned on your own trajectory plan. And this is really trusting that your prediction model right now, which is usually fixed and trained offline, trusting that that prediction model is good. There's a bunch of people working on making these prediction models very good. And so I think that's part of it. But the other part that's really challenging is usually the prediction models are large and heavy. And if you want to incorporate that within some MPC framework, you're differentiating through the outputs of a neural network at every iteration of MPC solver. So there's a numerical challenge besides the fact that you're also trying to avoid non-convex sets that are usually represented in a nonlinear fashion at runtime. So I think that in terms of your question, absolutely, I'm definitely looking at more complex notions of safety, and that's the right way to go forward. The reason I focus on even static collision avoidance in this talk is just to say that on its own, that's still very nonlinear, very not convex, and hard to, if we can handle that one, it gives us promise that we can handle much more complex constraints.
Thanks.
Thank you, Anna. Any other question? Yes, Chizeng, you can go.
Hello, Shreyas.
Hey, Colin.
Thank you for the very, very well well-rounded explanation of the 3 layers from the overall planning to the middle stage and to the very local MPC. So I remember you mentioned how the reinforcement learning as the overall planning outperformed your hand-tuned just RTD planning. Is that correct?
Yeah. So RTD was taking in waypoints from either RRT or A-star. And so I had to hand tune the RRT or A-star hyperparameters to get them to produce good waypoints. Replacing the waypoint generation with RL is one way to think about what RTS is doing. In fact, RTS is actually directly taking initial guesses of the solution to the nonlinear, non-convex mid-level program, but that's equivalent to guessing at a waypoint.
So then I guess my question is, recently I'm also looking at, there's a popular approach in teaching via demonstration. So because training, a lot of people again say that training reinforcement learning is quite tedious. Sometimes you think that you have successfully trained, and one failure you have to retrain again. It's so then they prefer, I'm just going to show you once and just do what I'm doing. Do you see that as a possible higher level planning strategy to implement with RTD? And
yeah, absolutely. And I would argue that the challenge in that space is that you can't create demonstrations or do imitation learning for every possible task that you might expect the robot to reasonably see. So there's additional work to be done in imitation learning, some general notion of skills that can be adapted to novel tasks at runtime. The cool thing is, as long as you have a low-level safety guarantee and you trust that your numerical implementation will actually enforce that guarantee, you can play with all kinds of different learning approaches at the higher levels. And then the longer term, most exciting part, and we are starting to work on this here at Georgia Tech, but can we actually exploit the safety layer? So it's not just learning how to mimic the human, but learning how to mimic the human in a way that the robot maybe doesn't exactly mirror the human's motion, but also leverages the fact that what the human asked it to do will put it into a more conservative part of the safety layer. So it may actually redirect itself to get the same task done while avoiding that overly conservative behavior. And that's, I think, genuinely challenging because often these are orthogonal directions, meaning like safety and performance are often at odds with each other, but this reachability way of thinking can start to bring them either fully aligned or at least closer together. Yeah, it's a very good question. Thank you, Colin.
thank you.
All right, any other question? Hannah, go ahead.
Yeah, so I can also ask. So because we're like developing Cora in our group, I was wondering if you have any suggestions on, because obviously you're talking a lot about like reachability analysis, to some extent conservative, because we always want to over approximate. Where are the tweaking points where you think we should put a lot of effort in to make them, I don't know, more efficient, or a better approximation or whatever?
Yeah, this is a really good question. And also, yeah, I appreciate Cora. It's a tool. Like you can see this plot on the right. So we're actually representing the reachable sets for the quadrotor with zonotopes that were computed in Cora. And I apologize that the talk wasn't, it would get very long if I went to the zonotope methods, but I have some cool slides on that if you want to see them later. And it's very much thanks to that Cora toolbox that has been developed in Matthias Althoff's group. So in terms of how to make it more efficient, it's very challenging. Actually, one of the directions that's been pursued a lot recently is more and more complex representations of objects that look like zonotopes but are not quite zonotopes. We've seen the trick is that as you get more complex to get like less conservative, you also get less or non-convex shapes that you can't collision check anymore. And I don't know where the line is on that. One fun project that we had was this thing that I called ellipsotopes. And it turns out some other people, I just learned yesterday, had proposed ellipsoid bundles, which are a generalization of it's a specific type of constrained polynomial zonotope that stays convex, but lets you express a much more general, like curvy shapes, unlike zonotopes. And honestly, like the way we wrote the code was really mimicking the Cora toolbox, because I think that the code base is nicely organized. So being very careful about the representation to keep it convex so we can use it within MPC frameworks or these reachability-based frameworks, that is one of the challenges, because it's immediately at odds with the conservativeness. Another challenge that I've noticed is actually, in general, collision checking reachable sets, usually independent of the representation, requires solving an optimization problem. So you can imagine that my reachable set is implicitly represented, and then I want to check if it collides with some other object. I have to solve some optimization that checks whether that collision is true, but that has to happen within an outer planning layer. So I have a bi-level problem to solve. One way that can address that is to unroll that inner program and fold it into the outer program. And creating that unrolling is somewhere that I don't know if Cora is really focused on this, because I think Cora is more focused on the reachable set computation, but less on how you use the reachable sets. But using the reachable set is genuinely challenging, and coming up with new numerical representations that allow us some analytical evaluation without having to solve an optimization program to check if we're in collision is, I think, really, really key going forward. For example, polytopes can be represented as an intersection of half planes. So to check if a point is within a polytope, you can just evaluate like one matrix operation and then a max. Versus checking if a point is in a zonotope requires solving a linear program, or converting the zonotope to a polytope representation and then evaluating it, right? So there's no free lunch here. If we get nice representations for reachability, we have very hard representations for actually using those reachable sets at runtime. Luckily, there's a lot of clever people working on this. So I think hopefully we'll come up with some interesting implicit representations of reachable sets that can let us do this collision checking more efficiently.
Thanks.
Thank you, Anna, for the question.
Yeah, thank you very much.
Any other question for Shreyas? I actually have a follow-up question to the first one Anna asked, which is, how do you think the interactions with other agents factors in your uncertainty quantification? I'm thinking really about all this. In the past years, there has been a lot of research in game theoretical frameworks, right, for motion planning. So how does it relate to what you're doing?
In terms of so if I understand your question, you're asking how other agents' motion may factor into the uncertainty in my own motion.
Exactly. Because so far you had like static obstacles, but
Yeah, or even in dynamic obstacles,
Yeah.
we assumed that we had perfect predictions, or at least conservative predictions, right?
Exactly.
And that's the standard assumption that you have to make to say anything about safety. I think that in terms of collision avoidance, our own robot, unless it's a drone that's flying very close to other drones or objects, our own robot dynamics are not going to be too affected. And so the uncertainty part is really not affected in these types of mobile robotic problems, and in the sense that we know pretty well what our robot is going to do. Where this uncertainty becomes really interesting is if you want to make contact or plan through contact with other moving people. So even like planning a handshake maneuver, right? Your dynamics change as soon as you make contact in that handshake, but there's some social custom and experience that goes into making it possible to do a handshake. Now, I don't know that I want to shake hands with the robot. I don't think that's necessarily the right way to go forward, but the reason I bring that up is that if we're really proposing to put robots near and around people, there's a lot of work being done on in-home robotics, or a robot that could load the dishwasher, this kind of thing. We as humans often communicate through touch, through social touch in these settings, and that social touch significantly affects our dynamics, or the interaction, the physical contact with the world is always changing our dynamics. It's very, very hard to model that in a way that is amenable to fast reactive motion planning with any sort of guarantees. I mean, it's hard to model it in the first place. Forget about making guarantees. So this is something I think is it's very challenging, especially because the ways we do it is usually through learning, and then you throw all the guarantees out the window. But and kind of to the question earlier about imitation learning, creating an example, like I think I could coordinate with you if we're both working in the kitchen. I could very easily coordinate to carry a hot pan around you without necessarily explicitly communicating it through some implicit contact-based communication, like I could, pat you on the shoulder or something. That kind of communication requires a larger semantic and contextual understanding that will, it does filter down into the lowest level, like actual tracking control, to use a dangerous phrase to describe human motion, but actually modeling that distillation of high-level task into low-level control is, I think it remains an open numerical challenge.
Okay, yeah, makes sense. Thank you very much. Any final question for Shreyas? Doesn't look so. Well, thank you again, Shreyas, for the great talk, and also good luck for the next steps for your start at Georgia Tech. I think there are a lot of very nice and interesting challenges ahead. And thank you all for participating. See you all next week.